everyone, and welcome to a new topic, new discussion, which we are going to have altogether a new technique, which is LiDAR technique, and also we will be seeing some applications of LiDAR. Some people call as LiDAR, some people call as LiDAR, and this is again ranging technique. So, what if we see the definition basically, also sometimes it is called 3D laser scanning. Currently it is little expensive, but with the time, the instrumentation and other things, it might become cheaper also. So, it is not only replacing conventional sensors, but also creating new methods with unique properties that could not be achieved before. So, there is no other remote sensing technique like radar or your visible or infrared, thermal infrared. So, this is basically complementary to that, and ground based LiDAR are very popular, though we will be seeing some airborne radar examples also. But this for 3D laser scanning, creating a 3D view of any building or mountain, landslide, all those purposes LiDAR is being used, which stands for basically light detection and ranging, and this is basically ranging laser based ranging technique. So, it is extremely useful in atmospheric and environmental research as well as in space exploration, and it is also has wide applications in industry, defense and military, and also in natural disaster, which we will be seeing some examples. And it has terrestrial, as I mentioned, that ground based LiDAR, it started basically ground based LiDAR. So, a lot of development has taken place in the terrestrial part of ground based LiDAR, then of course airborne also, and some mobile applications, that means on a vehicle they are installed and scanning is done. So, in the LiDAR like here, what we are seeing here, that this is the echo waveform, and when it is sent, this is outgoing pulse is here, and when it interacts with the say different vegetations, and then you get different waves which are created, like first level canopy, second, and then second level, and then finally it touches the ground. And this is how the returns which this detector receives after getting here. So, of course, time is the main function here. So, the first return which is the top of the trees, and then second return is the middle where the canopy structure is about to finish, only the trunks are there, and last return when it is at the ground level. And as you can realize at this time also that when this situation, that it can detect top of the canopy and above the ground also, then it becomes very useful to get rid of even your vegetation from your terrain and only get the terrain surface. So, this is how the LiDAR surveying method basically measures the distance to the target by illuminating the target with the pulse laser light and measuring the reflected pulse with a sensor. So, in that way it is more close to your radar technique, and the differences in laser return times and wavelength can then be used to make digital 3D representation of the target, as we are seeing here that there will be changes when it interacts with the ground features. So, the range which is given here is equal to C delta t by 2, because half of the time or the change in the time by 2 is taken, and C is of course constant. So, each time the laser is pulsed, the laser generates an optical pulse, that is the light, that is why it is light detection. So this is the optical pulse, and pulse is then reflected off an object and returned to the system receiver. And then high speed counter measures the time of flight from the start pulse to the return pulse, and by this the time measurement is converted to distance, and that is why it is called the ranging technique. And the distance to the target and the position of the airplane is then used to determine the elevation and location. It may not be airplane. If it is terrestrial lidar, which is very common, then that surface, and instead of rather than ground and aircraft, it can be the instrument itself and a surface, that may be a mountain slope or any other feature. And multiple returns can be measured for each pulse, because multiple returns depending on what objects. Then example I have shown you, that top of the tree, in the middle, and then from the ground also you can have the returns. So up to 200,000 plus pulses per second are possible with the LiDAR, and with everything that can be seen from the aircraft is measured, or ground based LiDAR which are fitted on a tripod can also be used. This is the example which is being seen, and a 3D scanning is being done through this animation. This is on a tripod, and if you put in front of a mountain slope or a landslide, in a few minutes time it can scan the every part at a very high resolution, even if it is covered with vegetation. And through the processing which we will be seeing, that this can the vegetation effect of vegetation can be removed, because it records not only the top of the vegetation but the ground surface as well. As you are seeing here, that every object whenever it is interacting, it is getting recorded, and this is what you are seeing in here also. So different pulses are getting recorded. Basically a LiDAR system involves a laser range finder which is reflected by a rotating mirror, as you are seeing here. It is being done, the top, the blue part, and then laser is scanned around the scene which is being digitized, and in 1 or 2 dimensions, and basically middle gathering distance measurements at specified angle intervals. So the user specified angles are chosen, and then you can define that how much area it would be scanning. In this example, it is going for 360 degree, but need not to be 360 degree. It can be only say in 30 degree or 40 degree, 90 degree. So it will cover only that much area, whatever the objects which are present, it will scan and create a 3D. Now LiDAR is commonly used to make high resolution maps, because it can provide you millimeter resolution data, and that is why it can create high resolution images, high resolution maps, which has got application in geodesy. Any movement, if suppose a landslide or a sloping slope of a mountain has been have been scanned on one day, and after say 1 year again that is scanned, then whatever the changes on that slope has occurred can be detected. So it is used for the geodesy, that is the movement of the part of the earth or slope, and of course in the geomatics also it is used. In archaeology, people are using extensively nowadays the LiDAR, maybe for there are some minor deformations which may not be visible to normalize, or may not be visible in other remote sensing techniques. But if successive LiDAR maps are created or 3D models are created of a monument, historical monument, archaeological monument, then probably we can detect the changes or deformations which might be taking place. And I understand, like for Taj Mahal, this LiDAR technique is being used so that we can exactly know what are the deformations, though they might be very minute, maybe sub-millimeter deformations if taking place, but because of archaeologically a very important monument, such surveys are done or must be done. And then also in geography, in geology example I have given about landslides, or in mining also it is being used in extensively. Landforms modifications, deformations which might be taking place. Again, LiDAR is used in seismology, also it is used ground deformations which takes place induced by an earthquake or some other reasons. Then in forestry also, because the advantage with LiDAR is that you can detect different types of vegetations also, or remove vegetation from the terrain. So in forestry also it is being used. And then in atmospheric physics, laser guidance. Laser guidance is very common, like when this English, when this tunnel between France and England was created, that is through English Channel, and the guidance was done through laser, this LiDAR technique, so that whatever is the drilling which is taking place, excavation is done, it is all perfect. So there are a lot of tunnels which are created for different purposes, for transport or maybe for hydropower projects, and there laser guidance is required and LiDAR technique is used. And of course airborne LiDAR is also for swath mapping, and laser altimetry is also done, so that one can get the elevation mapping also through LiDAR. So various applications, many more. This is not the exhaustive list. Many more will be coming also in near future. And the technology is used in control and navigation for some autonomous cars, and that is again a lot of development is taking place, and that driverless cars, for which again for navigation and control these laser technique or LiDAR technique is used. And it is also wide application in industry, defense and military. And sometimes we don't know much about these two domains, but nonetheless overall where in the civilian domain things are being done, almost there also, and plus more things are being done. It has terrestrial, airborne and mobile applications which we have already discussed. Now when we go for aerial, we will be seeing also example this ground based or terrestrial LiDAR, but here what we are seeing airborne LiDAR, and say through this figure what we can see that the line by line, it is scanning is been done like this, and once it completes, then a point data is created, or that is giving different heights also. So it has been colored based on the height. So top of your trees which might be there, forest cover, you are seeing in red color, then yellow, then green, and of course ground surface is in blue. So in that way, and all these things have to be corrected. There, if you recall the geometric distortions in satellite images, so as in geometric distortions, we discuss about roll, we also discuss yaw and pitch, and many more, many distortions which occur due to the movement of an aircraft and variation in the air density, and all these have to be corrected before we employ this data for even for creating a digital elevation model. So all these are also shown here, roll, yaw, pitch, and many things nowadays are controlled through GNSS. So those are also our 3D LiDAR equipments are always having a GNSS receivers by which we can also have controls over lot of things. So in aircraft, then if it is aerial LiDAR, then you are having aircraft, you are having a scanning laser emitter receiver unit, because both the things will be done by that unit, and then differentially corrected GPS, or in this we can say GNSS, which is highly accurate, and then you are having inertial measurement unit, that is IMU, so that same time it is recording the movement of aircraft, and roll, yaw, pitch, all those things are also being recorded. So later on, and that information or those information can be used to correct our data, and this point clouds basically. And then of course for recording purposes and recording other data sets, a computer is also there. So there are basically 5 components of a aerial LiDAR system, starting from aircraft for the recording up to the recording system. Now the scanning mechanism, as also shown through earlier in a ground based LiDAR or terrestrial LiDAR, that you are having a oscillating mirror, and there also you have seen, and then you are having sawtooth, that jet shaped sinusoidal data, as you can also see here that the sinusoidal data is here, and then you are having rotating polygon like this, and then parallel lines are also created, and there might be another way of doing is a nutating mirror and Palmar scan and elliptical, it is also done. So most common one either are the oscillating mirror or rotating polygons, by which we can create parallel lines of those points, which are later used to create surface or any other thing. Now how this determinants of LiDAR data characteristics basically. So here because not only it records the top of the canopy, but also it records in between, and then of course the ground surface is also there. That's the biggest advantage with this kind of remote sensing technique, where the canopy height can also be determined, and because of the penetration which sometimes may become in a dense forest condition may become difficult, but otherwise it is possible. So when you get this data which is a combination of a scanner system and which relates to the beam pattern, what kind of beam, laser beam is being used, and then flight altitude, the height of the aircraft in case of airborne, and there might be some limitations also. Then pulse rate, at what rate the laser pulses are being emitted by a sensor, and then scan frequency, how how frequently that mirror or polygon mirror is being used, so that that will decide the frequency as well. And what is the angle here? So two angles like in this example are shown vertically downward, that is nadir view kind of thing, and then off nadir also, and then possible maximum around 30 degree it is possible. But at the same time, because one has to remember that the aircraft is moving, when it sends the pulse it has to collect also. So everything has to be synchronized in a manner that the return beam is also collected by the receiver. It is not just emitting and going, it is collection also. And then scan swath, how much area has to be covered, which will depend on this possible maximum around 30 degrees scan swath. Now when we get the return, that raw data return is having x, y and z points, and these are at a very high spatial resolution, and laser footprints on the ground may be of even less than 50 centimeter, and that is why high spatial resolution is possible. Typical density of these pulses can be 0.5 to 20 plus pulses per square meter. That is why we can achieve a very high spatial resolution data, and 2 to 3 return pulses in forest area, and that is possible because of depends on the density of forest. And surface canopy models typically 1 to 5 meter grid is possible, and that's the biggest advantage, as I have been mentioning about that it can also detect the top of the canopy as well as the ground surface. The one can say as a negative with the LiDAR is the large volume of data. It creates hell of data, lot of data to process, and because of lot of other things are to be considered, the movement of aircraft and angle and pulse rate, frequency, everything. So the processing is really challenging in case of LiDAR. But nowadays there are commercial softwares, equipments, and all kinds of things are available by which it has become possible to create digital elevation models or study a landslide movement or a monument with the terrestrial LiDAR or airborne radar. So 5,000 to 60,000 plus pulses per hectare, that kind of volume of data we are talking. 10 to 100 plus thousands of return per hectare. The return is going to be of course less than what you transmit or emit, and then 0.4 to 5.4 plus megabyte per hectare data, that kind of data we are talking. Of course, these things will depend on the frequency and the resolution which one has chosen, and the scan view, the swath, and other things. Now, in the return density, which is the data, which is the real, the recordings by the receiver, is that in the footprint size decreases with increasing post spacing, and importantly, the last return from a discrete return system is not always the ground. So this is a sort of one limitation, that whatever the last return, it may not be always the ground surface. It may be from even the base of canopy, or maybe from some other surface as well. So LiDAR system and sensor systems vary in number of returns from a surface. One example is shown here, that here this is the first return which is coming. Then you are having in second return, you are having many point data is there, and then in the third you are getting just very few here. So likewise you get the data in that. Now there is another thing which has to be considered, is the reflectivity, because ultimately the pulses which are sent towards the ground or towards the slope or any building has to be returned. It will depend on the reflectivity. So these highly reflective objects may saturate some laser detectors, while the return signals from low reflectivity objects may occasionally be too weak to register as valid signals. So that kind of different materials are shown here, and their reflectivity at the rate of lambda, which is generally used at 900 nanometer, wavelength 900 nanometer, and what you see is that if you are having pine or a tree, or you are having clean or dry surface, 94% reflectivity is there. If you are having black rubber tire wall, then the reflectivity is 2%. If you are having volcano lava, maybe 8%. And like deciduous trees will have a different reflectivity. Coniferous trees will have a completely different reflectivity. So, based on the reflectivity also, one can use to detect different objects also. So, minimum detectable object size depends on reflectivity and also the resolution which has been selected. So, a strong sunlight reflection of a highly reflective target may saturate a receiver and may produce an invalid or less accurate reading for the recorder. So, that may create, and most acquisition is done in a preferred range of angles to avoid this issue, so that the sunlight direct reflection does not come during the these kind of data acquisition surveys. And there are some other distortions like in normal remote sensing, like dust and vapors can also bring some distortions, and especially these may create problems in airborne radar or even in terrestrial radar if they are being used in mining or in a tunnel or other excavation. So, because of high dust density, so these laser measurement can be affected, weakened by interacting with dust and vapor particles, and because of scattering of laser beam and the signals returning from the target. So, two ways it will affect, because when emitter is emitting the laser beam, during that time it can become weak to reach to the reflecting surface, and when return beam comes to the receiver, again it has to pass through the same dust and vapors and can create weak signals. So, using these last pulse measurements which can reduce or eliminates this interferences, some corrections techniques are there by which this scatter effects of dust and vapors can be minimized, and it is expected to work in such conditions regularly, which can be optimized for these environments. So, if systems have to be used regularly in, say, in a tunnel which is full of dust or maybe water vapors, then these things can be optimized depending on the environmental conditions there. There might be some background noise and radiations which may again affect your laser. So, though generally laser is not affected by background noise, but most system determines baseline radiation levels to ensure that it does not interfere with the measurements. Now, accuracy. Overall accuracy, that is XYZ position of each return. Of course, these are very general terms. These two accuracies, horizontal and vertical, are given, and these are improving. So, one may find better systems, better results with these accuracies. But what accuracy you get in return is 50 to 100 centimeter in horizontal and 10 to 15 centimeter in vertical. So, suppose somebody has gone for a digital elevation model, then 1 meter spatial resolution digital elevation model can be created, and that digital elevation model will have accuracy of 10 to 15 centimeter, which is anyways very high compared to what we get through normal remote sensing techniques. So, in that way it is definitely, of course there are limitations, and the cost effectiveness should also be seen when we compare these two completely different techniques. And this is one advantage which I have been mentioning repeatedly, that the bare earth surface, it is possible with the airborne radar that we can have a digital elevation model without any objects, without any trees or other things. So, that is the bare earth surface can be created without these things, Tree heights can also be determined with a very good accuracy of 0.5 to 2 meter. And of course, due to different types of trees, that species dependent. So error is basically a species dependent. If it is conifer trees, it is different reflectivity, different accuracy. If it is deciduous trees, it is different reflectivity, different accuracies. Now, few examples of digital elevation models are shown here based on radar and with comparison with the INSAR or IFSAR. Like if I start with the top right, that is 10 meter USGS digital elevation model. Though this digital elevation model is not available at global scale, but this figure we can still use of part of US. And what we are seeing for the LiDAR, what we are seeing that this is also having the vegetation cover, which you can see in the this right middle figure. And then if I involve the IPSAR, then this kind of digital elevation model one gets, that is based on the radar technique, interferometry techniques. And the LiDAR can create a surface or bare ground surface. So here this is the input image, and then you are seeing here the DM which is, so on left side you are having digital elevation models, also this 10 meter on the top also. But then these two, this one and this one, are the canopy models of the same area. As you can see, in case of LiDAR based digital elevation model, many ground features or landforms can be identified very easily. Like here, the streams, individual streams can be identified, which is not possible in this example by using IPSAR, or of course not with 10 meter spatial resolution USGS DM. And if you are having canopy cover, of course everything is hidden beneath the trees, so that cannot be either detected. And now what you are seeing also the landslide in LiDAR, detection of landslide, which is again not possible in IPSAR DM or 10 meter USGS DM. And of course, when you are having canopy models, you don't see any such landslides either. So the advantage with the LiDAR, as you can realize, is very clear that these are the things which otherwise one would miss in other techniques is possible to detect using LiDAR. This is a blow up of those things that individual streams can be identified here, and same with the landslides, that very clearly one can see a landslide when you blow up that part of a digital elevation model that is in 3D perspective. So careful study of such surfaces can give you the idea of such a slope movement as well. So it has got really very good application. Now what are the LiDAR products which are available, can be made available, though on a global scale such things are not there, like digital orthorectified imagery are there. Some LiDAR also provide digital color and black and white orthorectified imagery simultaneously with this point clouds. And then of course intensity return images are also created by the LiDAR. LiDAR derived products are many. One example you have already seen, the digital elevation models. That means once you are having the data, you can drive a digital elevation model at a very high spatial resolution and relatively a very high, with very high accuracy. Digital terrain models, and this is the digital elevation models which are created using your conventional remote sensing or radar remote sensing, and those are having whatever the on the surface of the earth, on the ground whatever the elevation values are having that part included. But here this bald or bare ground elevation model is possible, as you have seen earlier in the example, that here what you are seeing, that without canopy a bare ground digital elevation model can be created. And then of course tin, which is again a representation of a surface, continuous surface, can also be created, because originally LiDAR collect the data in point form, and using these points one can do the interpolations, and one can use these points to create a tin as well, triangulated irregular network, which we have discussed in our earlier lectures. And break lines also, which are line representing a feature that one wish to preserve in a tin, maybe a stream or a ridge or a fault line. Those things can also be detected quite easily, can be derived from LiDAR products or LiDAR data. Of course, once a digital elevation model or DTM, a digital terrain model, can be created, so contours can also be derived out of that. And once you are having this digital elevation model or DTM, you can also derive your shaded relief model or hillsides. And there are a lot of derivatives of digital elevation models which are discussed in GIS lectures or course. Very early outputs of a digital elevation model, or first outputs of DMs or DTMs, are slope and aspects. So here also one can derive those as well. Now one example here with the canopy, which you are seeing after laser survey, this has been created, and since the data is because it records not only the top of canopy but middle and the bare ground also, whatever is get the late return or last return, and using that you can remove the vegetation completely. So here the with the vegetation or with canopy, the terrain is with canopy, and once that is removed, then you get this you can call as a DM or a real terrain condition, and this is a completely digital terrain model without any canopy or without any other features. So completely walled or bare ground surface, and of course this has been, and this is a shaded relief model, and it's being shown here is a 3D perspective. But if one is studying doing some watershed management or any kind of work, one would love to have a terrain surface without any objects like vegetation or buildings or any other thing, and this is how it is possible employing LiDAR technique. Now indirectly we have already discussed the sources of errors in LiDAR data, but for completeness we will be going one by one about the sources of errors in LiDAR data. The similar things are also in normal remote sensing, so many sources of errors are also common here. Nonetheless, during acquisition it is possible any wrong selection of swath or angle or anything that may result into the errors in your data sets. Processing may again create some errors, like stripe adjustments are there, because after all if it is airborne, then it has the object or the sensor is moving. If it is terrestrial, then it takes the angle maximum maybe 30 degree, and maybe during if I have to cover a very large area which cannot be covered in 30 degree, then there might be some adjustment, mosaicing and other things may create some errors. So selecting ground control points, GCPs, again the error might be there because of for requirement of georeferencing, and the thinning or making generalization in the data may also create some errors, may bring some errors in our data. Interpolations, of course, because the data is being collected as point data, so many times the choosing a wrong interpolation techniques or any interpolation technique may bring some kind of errors in the data, in the results. And of course, at later stages of analysis and visualization, and there might be some errors are there. Errors might be due to scan acquisition scan angle as shown here, that because if it is sloping surface, then the angle may create different kind of appearance of objects, and that may create some errors in the data. So, LiDAR data should be acquired within 18 degree of nadir, and so we cannot go beyond this angle because the LiDAR footprint can become highly distorted as shown here in this example here. And as this angle is more, the large error will erupt in our data set. Complex terrain can exacerbate the problem. This problem can become bigger in terrain like Himalaya, which is a highly rugged undulating terrain where things can become very difficult. When we get the data, this strip adjustment can also be there, and that may bring some errors. So, there are systematic errors. Again, systematic errors can be corrected easily, but there are some non-systematic errors, and which is difficult. Also, if we are using GNSS and that is not giving good accuracy, and then that can create problems by doing the processing or pre-processing of the LiDAR data. This movement, aircraft related movements can, all aircraft related movements cannot be fully corrected. So, they may leave some error in our results also. But as you know that point cloud will not lie, so on ground, but it is offset in planimetric view and height, and that can create a problem. And there are ways to some extent that these errors can be removed, and that discrepancies strip adjustment algorithms require basically quantification of these offset at various locations. So, lot of if one go for a very accurate output or results, then lot of other data sets are also required, and those data sets have to be recorded during the acquisition of original survey. That one has to remember. So, improvements are basically needed as we go for automatic tie or ground control points detection and 3G adjustments. Manual effort and labor are time consuming. If we are having non-systematic errors, then these problems will come. Ditches and ridges are useful, and which can help us to remove some of the errors, and improves planimetric accuracy by 40% and height accuracy by 25%. So, these can be created to limited errors, but 100% errors cannot be removed all the time. And data correction and quality control tools are there, and which can be employed. Now, selecting ground points like here, say mixed kind of data collection is there. So, whether you would select this much area like here or only this much area. So, that is basically will go ultimately in your results. So, the slope threshold applied to the urban areas as in this example, and depending on the requirements. So, active area of research, how to make LiDAR technique more accurate, more reliable, and less less expensive, cost effective. Many algorithms are being developed to improve on this, and there are many times project specific things are being developed, and of course manual cleanup also necessary in many cases to remove the errors. Now, one of the examples here is that you are having a completely forested part, one can get rid of certain objects then, and finally completely bare ground digital elevation model can be created of that area. There are some other processing techniques like in our normal digital image processing techniques, filtering, here also filtering, but of different kind, that once this ground point selection is done, the filtering is performed to reduce the size of data sets, and this type of filtering should only be applied in even terrain. But if terrain is highly rugged, then such filtering is should not be applied, because in highly rugged terrain each and every point is important to preserve the ruggedness of a terrain. But if it is a flat terrain, then there might be redundancy in the point data, and therefore some kind of filtering technique can be applied to reduce the size of the data. Uneven terrain and densely vegetated areas are most susceptible to removal of critical interpolation points, and there one should not really apply the filtering. Now, digital elevation models and digital terrain models where the ground is so here when say digital terrain models, the ground part is here, otherwise in digital elevation models as discussed, it is having also canopy cover. There is another term which is used also in GIS, which is called digital surface model, that is the top surface, that is above the canopy, and the digital terrain model is below the canopy. So when we want to do some serious things on using ground surface or terrain model, then this DTM is the most useful and reliable than a digital elevation model or DSM. Using LIDAR based airborne surveys, it is possible to create all three, that is DEM, DTM and DSM, whereas DTM, and that is digital terrain model, that is the bare ground surface, is the most important in many applications. In open terrain where you do not have a lot of ruggedness, the separation between the surface between air and bare earth is good, and then DM is different from measured laser point due to very different reasons. Filtering, classification of points into terrain and off terrain, and then basis of DTM generation, that is detection of topographic objects. Like here there might be that they are using incorrect scale, and over smoothing has been done for the terrain, and here the interpolation error which has shifted this tree, instead of here it is here. So, lot of errors. Many algorithms are there which propagates inherent error in the data. That is always true, that error propagates in processing also, and sensitivity to spatial distribution and local lack of points, ground control points. If those are not there, there might be errors, something like this which you are seeing here, and can introduce some artifacts also during the interpolation. Here is one example of mapping forest attributes across a landscape. Here stand height at a capital forest site is 30 meter per cell, and what you are seeing, the stem volume is 30 meter cell here. So this one plot which is marked here will give different results across different landscape. But here we are seeing that mapping forest attributes across a landscape. So one area has been, so here the forest, capital forest, and this is the stem volume, how much volume, that can also be calculated using LiDAR technique. There are some other few more points which we need to discuss related with LiDAR. That the digital elevation model which we drive using LiDAR are not often hydro connected as to ensure the continuous downward flow of the water. In a digital elevation models which are created using different techniques in normal remote sensing, sometimes they are having these issues are not as big as in case of a LiDAR, that is hydro correctness of downward, because digital elevation models are used for surface hydrologic modeling, and in which it is assumed that whatever, even a single drop of rain, if it occurs, it will flow to an outlet. So that means the surface which is being created based on LiDAR should have that characteristics, and that it should be hydrologically corrected. That means the water should flow downward to the outlet. So these things are important while using digital terrain models or digital elevation models which have been created through LiDAR technique. Because if water is present on a surface, then water creates a natural void in LiDAR because of absorption of LiDAR beam, and manual addition of braid lines is necessary. That means manual correction sometimes may require in your data set, and this type of processing is possible with LiDAR, but it definitely it is time consuming, may require some techniques, and it will add some cost in it. Now few examples are here. Airborne LiDAR bathymetry is here, high resolution which is bathymetry technology, very high resolution multi-beam LiDAR map showing spectrally faulted and deformed sea floor, which you can see here, and of course it is a colored shaded relief model. It has been shown in that form. So definitely the surfaces which are created with LiDARs are highly useful because of high spatial resolution and high vertical accuracy, whether it is for surface or for under the water, as here the bathymetry example is shown here. I was mentioning about a very small mention was there in the beginning while discussing about the applications of LiDAR is in case of autonomous cars, or this is that example is here, that the cruise automation or driverless cars in which LiDAR technique is being used extensively, and lot of research world over is taking place that how to make vehicles completely driverless, employing all kinds of techniques, not only LiDAR but GNSS techniques, GIS techniques, and many communication techniques. And so that and the first, of course, the essential condition here is that no accident should happen, and there should not be any harm, and neither to any human on the road or structure or to the car. Those are with those conditions such autonomous vehicles are being developed, which is fine examples of integrated technologies, including, as I have mentioned, LiDAR, including GIS, including communication, and of course GNSS technologies. So this is one of the example Google has also developed. This is another example from that one. And now we will be just going through a quick comparison between traditional photogrammetry versus LiDAR, because LiDAR is a laser based, so therefore it is possible to do it in day and night time, whereas traditional photogrammetry is done only in daytime, and direct acquisition of 3D collection is possible with LiDAR, but in case of photogrammetry it is complicated and sometimes unreliable also because of lack of procedures and other things. Of course, vertical accuracy in case of LiDAR is very good, especially then better than the planimetric accuracy, and vertical accuracy in case of photogrammetry can also be good. One of the examples of satellite based photogrammetry is using stereo pair data and creating digital elevation models. There, that is the satellite based, but the ground based photogrammetry techniques are there, aerial photogrammetry techniques are also there. And in case of LiDAR, this is point clouds, which is difficult to derive semantic information. However, intensity values can be used to produce visually rich image, and like product example of intensity image can be created using LiDAR, but photogrammetry is definitely rich in semantic information. Now, intensity image example is shown here, and that LiDAR intensity can be used here, like in your radar remote sensing also intensity images can be used. So, this is a generally unused byproduct of LiDAR acquisition is the intensity of the object, and that the pulse is striking, and this is uncalibrated. The example here is in 8 bits image, though it is ortho rectified, and can be used as ortho photo for any other applications. However, it may be unsuitable for any kind of quantitative analysis, because as the image gains always set as adapted gain settings when images are acquired. So, these are having some limited applications there. Now, there are further analysis which can be done using LiDAR based products. Once the DM or DTM are available, and then one can employ these in GIS for further analysis, systematic and other modelings, systematic analysis and modeling. Accuracy assessment is always challenging in every technique, so in LiDAR, and that should always be attempted. One accuracy assessment technique which we have discussed while discussing the supervised classification also. So, everywhere that has to be done, so that and the best way, like in supervised classification, ground truthing or ground validation, so here also ground validation will require. So, this brings to the end of this discussion about LiDAR applications, limitations, and error part, and how these can be minimized. And main is, as mentioned, that LiDAR provides a bare ground surface which is very useful in many applications, and that too at a very high spatial resolution and very high vertical accuracy. However, the cost is one thing, and availability is another limitations, maybe limitation in certain projects. So, this brings to the end of this discussion. Thank you very much.